Welcome back everyone. In this lecture we will actually study the space of bilinear forms on a given vector space, and then we will relate this with the theory of representations of G. So, let us actually begin with some general discussions. So, let us take V being just a finite dimensional vector space. Again we will work over only complex numbers. So, we can actually construct the space of bilinear forms. Let us denote it by BAL of V. So, this is the space of all bilinear forms on capital V. So, what does it mean? That means it is a map from V cross V to C. It is linear in both variables. Okay. So, there are two variables, first and second variable. So, in both variables B is actually just linear. So, one can also actually talk about K bilinear forms, okay, but here we are going to only talk about two variable bilinear forms, K linear forms. Here we will talk about bilinear forms. So, now we have this natural actually isomorphism between the bilinear forms and this home space. So, if we take this bilinear forms, so then we can easily find this natural isomorphism between home V comma V star to this bilinear forms of V. So, what is this natural map? So, given any B, you just map to what is called this B tilde. So, which is a map from V to V star. So, it is the evaluation map, basically this is the evaluation map. So, you basically evaluate, take the evaluation. So, that means you take V and then send it to B V comma dash. So, this is the evaluation with respect to this map B. Okay. So, this is indeed isomorphism. So, that is easy to verify. Okay. So, I will leave it as exercise. So, this is a vector space isomorphism. So, now what we are going to do, like we are going to actually use this natural isomorphism and then define G action on this BAL of V if we start with the module V. Okay. So, suppose V is a G module, then that implies that this home V V star is a G module. Okay. So, that is because, so again this is all C linear maps from V to V star. So, V is G module, V star is G module. So, home V comma V star is G module. So, now use this isomorphism, and then using this isomorphism just pull back the action of G to this BAL of V. Okay. So, the pullback if you just work it out, it is going to be, okay, or you can actually directly verify. So, we have this G action, G act on this BAL of V via this following assignment. XB is defined to be XB of V comma V dash is exactly equal to minus B XV V dash minus B V X V dash, and this is for all V V dash in V and X in G and B in BAL of V. So, this is the formula that you get if you actually pull back the action of G that you define on this home V comma V star. So, I will leave it to you to check, or one can directly check that once you define this G action using this star, then BAL of V becomes actually G module, and the natural map that we have defined here, this evaluation map, this is indeed G module isomorphism. So, this is a G module isomorphism. Okay. So, now we have the following isomorphisms. So, this BIL of V, so it is naturally isomorphic to home V comma V star as a G module. Okay. Now, this is, you know, that it is naturally isomorphic to V star tensor V star. So, this is again G modulus also. So, recall, we proved that if you take V star tensor W, that is naturally isomorphic to home V comma W. Okay. So, that is why you are getting this isomorphism. Again, this isomorphism is also like used, there is a natural isomorphism as vector spaces. You can use the action of G on the left side to pull back the action on the right side. That is how you write down the formula for the home V comma W. So, that is similar techniques that we will use here as well. So, now let us actually try to understand this isomorphisms, but before that let's define some important terminologies. Okay. So, given a representation, we can always talk about what is called invariant vector. Okay. So, let me just make a side note. So, if V is a G module, then a vector, okay, V in capital V, again we want it to be non-zero. So, 0 means it is okay, it is already invariant vector. So, given a non-zero vector is said to be invariant vector if the action of G just kills this vector. So, that means it should be in the kernel. Okay. There is this natural map that is defined from G to GL of V via the representation. Okay. And if you take this vector V, okay, so that should be killed by all the images of this G. Okay. If you take this X and then look at phi of X V should be 0 for all X in G. So, that means this V is in the kernel of this phi of X for all X in G. So, that is what called invariant vector means. Now, using this terminology, one can actually define what is called invariant bilinear form. So, here is the definition. So, G invariant bilinear form, which is very important notion. Okay. So, what this means? It is just a bilinear form which is actually invariant vector of this natural model BIL of V. Okay. So, a form B which is from V cross V to C is said to be G invariant if this is indeed actually invariant vector, okay, for the representation BIL of V. If we rewrite that, that means, so XB should be 0 for all X in G. So, this is if and only if we can see that XB, when you apply it on VV dash, that should be 0 for all X in G and VV dash in capital V. So, which can be rewritten as, when you take, this is exactly minus B X V V dash plus B V X V dash. Okay. So, this quantity should be 0. So, that means it is called G invariant vector, then this quantity you demand it to be 0. So, B X V V dash plus B V X V dash should be equal to 0 for all V V dash in V and X in G. So, that is what invariant form means. So, here is the natural characterization for this invariant forms. So, these invariant forms actually immediately gives us G module maps from V to V star. Okay. If we start with, so let me call it as exercise, it is easy to do. Okay. So, if we start with B being G invariant form, so which is invariant vector inside this representation, then if and only if, okay, you have this B tilde which is a map from V to V star, which is given by V to B of V comma dash. Okay. So, this map should be a G module map, is a G module. Indeed, the condition that we have here, okay, if you rewrite that condition, you get exactly this. Okay, let us rewrite and see. So, B x v v dash should be exactly equal to minus B v comma x v dash. So, what is the meaning of B tilde being G module map? So, that means if we take B tilde of x v, that should be exactly x B tilde of v. Okay. So, let us rewrite this. So, B tilde x v. So, this is again a form on V star. So, we evaluate on V dash and then C. So, this is exactly by definition B x v V dash, okay, because V is mapped to B of V comma dash. So, now on the other hand, what is x B tilde of V? So, when you apply this on V dash, so x B tilde, remember that how the action of G defined on the dual. Okay. So, then you can easily see that. So, this is exactly equal to x dot B applied on V dash on V dash. Okay. Because B tilde of V is B V dash. So, that is what it means. So, now if you think about it, x dot f of V is defined to be minus f of x v. So, this is how we do in the dual, the action of G defined on the dual. So, that means this is exactly equal to minus B V comma x V dash. Okay. So, that means you are demanding that this thing is same as this thing, B x v V dash is same as minus B V x V dash. So, that is why whenever B is G invariant form, then B tilde becomes G module map. So, it becomes if and only if. So, this is actually very important observation, this we will use it repeatedly. Okay. So, now we can go back to the general bilinear forms. Okay. So, we can define what is called non-degeneracy. So, given bilinear form is said to be non-degenerate, said to be non-degenerate. Then look at this B tilde. So, that map which is from V to V star given by V goes to B of V comma dash. So, this should be isomorphism. Okay. So, this is the definition of non-degeneracy. So, there are many characterizations for non-degeneracy. This is one of the characterization. Okay. So, for example, what one can actually prove. So, this B tilde being isomorphism, same as saying that. Okay. So, B tilde is an isomorphism, same as saying that. So, there is no element actually that is killed by applying this B V. Okay. So, B V comma W is 0 for all W in V implies that V is 0. Okay. It is indeed if and only if. So, these statements are equivalent. Now, if we take actually some basis and then look at its actually there will be a dual basis with respect to the form that is given by B. Okay. So, if we start with the basis V1 etc. Vn, so which is the basis of V. So, then there exists another basis which is the dual such that this B of Vi Vj star, okay. So, this is exactly going to be just delta H. So, there is another basis of capital V such that this is going to be exactly delta H. So, basically what one can say, okay, so maybe that there is another characterization which we will call it 3 dash. So, if you fix a basis V1 etc. Vn of capital V, basis of capital V, if you look at the matrix formed by this B Vi Vj, okay, this matrix should be invertible. So, this is invertible. Okay. So, all these actually are equivalent. 0 is B is not degenerate. So, you can take any one of them as definitions. Okay. The most important thing is this 3. So, we will actually prove the version of this, okay, but we will actually kind of do it for the symmetric bilinear form. So, then one can actually identify Vi with Vi star. Okay. So, let us prove that proportion. So, let us start with symmetric non-degenerate binary form. Symmetric non-degenerate bilinear form on given vector space V. Okay. So, then we can actually find a basis V1 etc. Vn of capital V such that when you apply this B Vi Vj, you get exactly the canonical delta H. So, here given basis you are able to find dual basis, okay, but here we are saying that there is a basis, it is a dual to itself. So, now the second statement, if we assume that B is G invariant, okay, so then we have this characterization. So, if and only if, so with respect to the basis that we have here in 1, with respect to the basis in 1, so look at the matrix elements that corresponds to the G, okay. So, look at matrix representation of elements of G. So, with respect to this basis, okay. So, all of them must lie inside SON, they all lie inside SON. So, let us prove this. So, the proof is by induction, okay. So, we have to just set up the induction, then immediately we will get that there is such basis. The second one is just rewriting the definition. So, let us prove. So, by induction we can assume that, okay, up to n minus 1 the statement, first statement is true. So, to begin the induction hypothesis, yeah, for the 0 dimensional space there is nothing to prove. So, that is 0 space, we do not need to prove anything. Let us assume that we have n which is greater than or equal to 1. Now, we just assume that B being non-zero form, okay. So, this is non-zero symmetric non-degenerate form. For 0 form there is nothing to prove, okay. So, since B is non-zero, so since B is non-zero, there exists V in V such that B of V comma V is non-zero. So, one way to get it, so we are working with the symmetric form. So, note that if we apply B V plus W V plus W, so this is going to be exactly equal to B of V comma V plus twice B of V comma W plus B of W W. So, just use the linearity and then rewrite everything. So, now this implies B of V comma W can be written as of times B of V plus W comma V plus W minus B of V comma V minus B of W comma W. So, that means if B of VV is 0 for all V, that implies B is 0. So, that forces that there should exist at least one V such that this is true. Okay. So, let us fix such V, and then we will define Vn to be V divided by alpha, where alpha is just a square root of one of the square root of this BVV. Okay. So, where alpha satisfies alpha square equal to BVV, and it exists because we are working over complex numbers. Now, it is immediate that B of Vn comma Vn is equal to 1, because this is exactly B of Vv divided by alpha square. So, which is 1. Okay. So, we have this natural vector. So, what one can do? One can take the perpendicular of that with respect to B. So, basically it is a subspace, those vectors W in V such that B of W Vn is 0. Now, since the form is symmetric, so this is same as B of Vn comma W, and since the form is non-degenerate and then we have chosen Vn such that B of Vn is 1 and looking at only the perpendicular of that. So, this is indeed n minus 1 dimensional subspace. This is n minus 1 dimensional subspace. Not only that, when you restrict B to this Vn pair, okay, so let us call it W. So, the restriction of B to this W is again non-degenerate. That is because we have looking at the perpendicular of V with respect to B. Okay, this is easy to see. So, now we have this non-degenerate again symmetric form. If you take, restriction will be symmetric again. So, you have a symmetric plus non-degenerate form on W. So, by induction we will have a basis of W satisfying the required property, So, that implies that if you just adjoin Vn with this basis, then that satisfies the required property. So, this way we prove that we have a basis such that B of Vi Vj is exactly delta Ij. Okay. So, now let us look at the second statement. So, B is being G invariant. So, that is by definition, just simply we can write that in terms of the basis element. So, the basis element that we just fix it from that the first statement. So, if we take B x V I V j, so this is going to be exactly minus B V I x V j. Okay. And this should be true for all I j and x in G. So, this is what G invariant means in terms of the basis element, and this is if and only if, obviously. So, now if you take this additional condition that B of V I V j being delta I j, and just take this condition, this is the star. So, then you can easily see that this condition star indeed can be rewritten as follows. The star can be rewritten as V j star x V I is equal to minus V I star x V j. And of course, this V 1 star etcetera V n star, it is the dual basis with respect to B inside V star. So, V1 star etc. Vn star is the dual basis, okay, of course with respect to B in V star. So, that is why this statement that we have in the star can be translated. So, this is just translated like this. So, this is the condition for the matrix of X being element of S by n, nothing else. Okay. So, basically what this condition says, if I look at jith entry of the matrix X, okay, of the matrix of X, of course, with respect to the basis V1 etc. Vn. So, that is going to be exactly is the negative of the ijth entry of again the same matrix, let us call it X B dash, where B dash is V1 etc. Vn. So, that means the matrix X B dash is inside S O n. So, that is the meaning of being in S O n. So, this proves that if you start with symmetric non-degenerate bilinear form, then you will be able to always find a basis such that this condition is satisfied, and one can actually translate G invariant being the matrix representation of these elements with respect to that basis lying in S O n. Okay. So, now we can actually go back to this natural isomorphism that we have in between V star tensor V star and then the bilinear forms. So, this is naturally isomorphic to home V star and then which is naturally isomorphic to bilinear forms. So, this is all G module isomorphisms. Okay. So, now there are some immediate operations that one can perform on the tensors. Okay. So, if you just do that, we can actually ask what it corresponds to inside this bilinear forms. Okay. For example, one can flip two tensors. Okay. If we take V tensor W, then it can be flipped to W tensor V. So, there is this S2 action. So, then we can ask what it corresponds here in the bilinear forms. Okay. So, basically if I take F tensor F dash, this is the simple tensor, then one can see that this corresponds to a bilinear form that is defined using this Bf dash. So, this is exactly the bilinear forms. So, which is defined from V cross V to V, V cross V to C as follows. So, this is Bff dash defined on V dash to be just f of V times f of V dash. So, there is this natural bilinear form that is associated with this simple tensor F tensor F dash. So, this is again easy to see. Okay. I will leave it as exercise. So, now you have this natural flip. Okay. If we take this V so let us take this V star tensor V star to V star tensor V star. So, we have this flip map. Okay. F dash goes to F dash tensor F. So, what this corresponds to? Okay. So, if you think about it, this actually indeed corresponds to taking the bilinear form to its transpose. So, you take the bilinear form B and then send it to its transpose. How the transpose is defined? The transpose is defined to be B transpose V comma V dash is just exactly equal to B of V dash V. Okay. So, that is the definition of transpose. Okay. So, this flip indeed just does this. So, this is again very easy to write down. So, now if you just look at this the decomposition of V star V star. So, this we already seen that this is actually indeed as a G module. So, there is this natural decomposition as a G modules. This is indeed isomorphic to sim 2 of V star direct sum the alt 2 of V star. Okay. So, now if we take the corresponding things inside the bilinear forms, then what the sim 2 should correspond and then what this alt 2 should correspond. If you think about it, so naturally the sim 2 corresponds to what called symmetric bilinear forms, the space of symmetric bilinear forms, and that is easy to define. And then this alt 2 corresponds to the space of skew symmetric bilinear forms. Okay, all these things are very easy to verify. I will leave it to you to check. Okay, again this decomposition is a G module decomposition. Okay, that is again very easy to verify. Okay, so we will actually continue with the bilinear forms in the next class. So, we want to actually kind of construct many interesting family of G invariant bilinear forms, and then we will use that later to actually prove the existence of Casimir element in the in SLN. Okay. And then we have already seen that the existence of Casimir element actually gives some element in the center of the universal mapping algebra, or it actually commits with the action of SLN. That is good enough for us. And then we will use that information to prove actually complete reducibility for finite dimensional representations of SLN. So, that is why this theory of bilinear forms becomes very important for us. Okay, I will stop here. We will continue in the next class. Thank you.